All right, everyone, hello and welcome to this week's installment of the weekly webinar series. We are so glad that you're here. My name is Amy Price and I'm the Outreach Coordinator at Parks College. I'm joined today virtually by Dr. Mark McQuilling, who will be showing us around the Wind Tunnel Lab. We are so excited that you are joining us from wherever you might be. Thank you for taking the time to virtually visit us and learn more about the mechanical and aerospace engineering programs at St. Louis University. In total, Parks College has programs available in aerospace, biomedical, civil, computer, electrical, and mechanical engineering, as well as flight science and aviation management and engineering physics. We hope that today you'll hear or see something that piques your interest. Before we start, I want to give you an idea of how this webinar will flow. I'll soon introduce Dr. McQuilling, who will be showing you around the lab space and sharing information about the mechanical and aerospace programs. He will then introduce Parks students, Justin and Jackson, who will share their experiences of being engineering students with you. And finally, we'll conclude with time for questions and answers. Throughout the webinar, please submit any questions you may have to the Q&A feature at the bottom of your screen if you're viewing through Zoom, or in the comments section if you're viewing through Facebook Live. And we'll do our best to answer as many of them as possible during the last 5 to 10 minutes of our session. Throughout this webinar, you don't need to worry about turning off your microphone or camera. You can hear and see our presenters throughout the webinar, but we cannot hear or see you. Finally, if you have any technical difficulties today during the webinar, please email parksevents@slu.edu and we'll help to address any issues that may arise. This session will be recorded and posted to our YouTube page in the next day or two, and you'll receive an email with that link when it becomes available. And now, with all of that housekeeping out of the way, I'm happy to introduce Dr. McQuilling and the Wind Tunnel Lab. Dr. McQuilling, I will turn it over to you now.
Hey everybody, thanks for joining us. It's a pleasure to be here and show you some of the cool toys we get to play with in engineering. It's one of the things that makes engineering so fun, right? We get to play with toys. So as Amy said, we are in our fluid dynamics lab, or a wind tunnel lab as people call it around here, and I'll show you some of the experiments and opportunities you have to actually see real life physics in front of you. But first I'll share my screen. I got a couple PowerPoint slides for you. In case you don't even know what mechanical engineering, is just yet. So engineering in general, just read along with me, involves the application of physics, science, and math to creatively improve the world around us, right? We get to change the world around us. Mechanical engineering specifically includes analysis of the structural and thermal fluid environments involved in product design and development of machines, typically related to stationary and moving systems, energy systems, let's see, I don't know why my name's popping up there, robotics, material processing, manufacturing, and economic environmental sustainability. But we also serve our aerospace engineering program here as well. So aerospace engineering is more or less mechanical engineering applied to aircraft, spacecraft, and rockets. So it includes the analysis, design, testing, and production of aircraft and spacecraft and related systems, like launch systems and things. There's two major branches of aerospace engineering: the stuff that flies within the Earth's atmosphere and the stuff that flies outside of the Earth's atmosphere. Aeronautical engineering flies within Earth's atmosphere, and astronautical engineering is a theory and practice of spacecraft and launch vehicles. So the equipment and the lab experiments I'll show you today deal with our fluid dynamics lab course in the mechanical engineering and aerospace engineering programs. And it also involves some aerospace lab experiments that you'll do in the the 7th semester of the aerospace engineering program. All right, enough PowerPoint. I'll take you and walk you around and show you some of the labs. So when you enter the room, what you see is this large subsonic wind tunnel there, right? That bad boy can go up to about 150 miles an hour. And the other thing people usually notice is all the aircraft models on the room. And what you're seeing there with all the aircraft models on the walls there is about 40 to 50 years. It actually goes all the way around the room. About 40 or 50 years of aerospace engineering senior design projects. And one of the things that's really special about our program is we not only design these aircraft on paper and with computer models, but we can actually stick them in our wind tunnel, all right? Stick them in that wind tunnel, and I'll show you the parts of the wind tunnel. And we can actually test the aerodynamic performance of the wind tunnel by, I don't know how well you can see that. Let me see. Amy, yell at me if you can't see something really well I'm trying to show. But you can see that those supports there sticking up out of the bottom of our test section in our wind tunnel. So you can actually make your aircraft you design in aerospace engineering, and you can stick it in this wind tunnel. Underneath the wind tunnel, let me scoot back here. That blue thing and that box underneath the wind tunnel test section, that's a 6-component balance. So we can actually put the aircraft in that test section, run the wind speed where we want. We can change the angle of the aircraft and do different things. And we can measure the forces on that aircraft directly so you can compare it to what your computational predictions were, right? So kind of a complete process where you get to not just design, but you actually get to test. You get build and test. That's one of the big things about all the programs at Parks College. It's really focused on not just design, but build and test, okay? I'm gonna walk you around and show you a few more experiments you have the opportunity to play with here. So here we have a flow bench. Maybe I need to scoot back out a little bit. We have a flow bench where you can see, how about I set this down, right? You can see this little circuit here. We have a compressor that drives air through this circuit, and the air goes through and down this apparatus right here. But what you can see right now in this vertical slot, it's just a flat plate. And on one side of the plate is smooth. On another side of the plate, it's rough with sandpaper. I'll scoot back in so you can see that a little bit. And what we're learning here is the difference in physics. That side's the sandpaper, that side's the smooth side. We have what's called a pitot probe. Oop, you can't see what I'm pointing at. We have a pitot probe right here that we can scoot close to the surface and away from the surface. And that pitot probe can measure pressures of the airflow next to that plate when the flow is in a laminar or smooth-like state with the smooth side. And then we can flip this around and measure the same type of profile and get the same pressure information that we can convert to velocity information on the rough side there. So you can get a difference, you can get an understanding of the difference between laminar and turbulent flows. Laminar and turbulent flows are the two main types of flows, and turbulent flows have a lot more mixing involved, a lot more velocity fluctuations. So when you're in a design situation where you're interacting with a fluid flow, it's really important to know if the flow is laminar or turbulent, because that has really serious implications for how you design the machine or the vehicle that works with that fluid. Another experiment we have with this flow bench is, oh wait, something cool. I want to show you something cool first. Can you guys see this stethoscope we have here? Trying to hold my laptop at the same time. The stethoscope here is plumbed up to its own pitot tube, and sometimes we can stick that pitot tube right in here and move it up and down, and we can tell when the velocity is turning from a laminar state into a turbulent state, because as the velocity fluctuations go over that pitot tube, you can actually hear the difference in the sound. It's a really rough sound from all that mixing. Something pretty cool we do. All right, here's another experiment where you can see this little channel right here that turns the flow. We can hook that up to the same flow bench up here, and it actually turns the flow, and we can measure the pressures all over this thing, and we can understand energy loss as a function of the turning radius and pipe flows. Okay, so engineers deal with a lot of types of pipe flows, so that gives you an understanding of energy losses due to turns. Okay, this apparatus here helps us understand something. Let me scoot back out a little bit. Helps us understand something about flow visualization. Okay, and inside this test section, so it's another compressor down there at the bottom that just drives air through a channel. And in here, whoop, we have a smooth ball and we have a golf ball. And golf balls have dimples, right? So what those dimples do, I would have the machine running, but it's so loud you couldn't hear me. But the smooth ball, the air comes over that ball in a laminar state, right? And it causes something called a big separation. I encourage you guys to look on YouTube about flow separation on golf balls, okay? And what the smooth ball does is a different behavior than what the dimples do. The dimples actually cause a lot of velocity fluctuations that make the flow more turbulent. So the golf ball with its dimples goes farther and straighter than the smooth ball does. And this experiment visualizes the difference in the flow quality because we have smoke generated down below. I don't know if I said before, but the smoke comes up and actually visualizes where the flow goes. So you'll be able to tell why those golf balls have dimples on them. And again, makes it go farther and faster. All right. Couple more experiments I'll walk over and show you. Over on the other side of our lab, I told you engineers deal with a lot of fluid flows. We have an apparatus over here that allows us to study pipe flows. Okay, so this apparatus, right? This whole pipe flow apparatus has different diameters of pipes and different measurement devices installed. And we have a bunch of tubes there that can be hooked to what's called a manometer. See these tubes? We can measure the pressures at different locations. Here's a diameter change. We can measure the pressure differences due to the changing diameter. And we can hook those tubes up to a device called a manometer, right? And that manometer right there, you can see the colored liquid. It's just water with some dye in it. When we hook up those tubes to these different pressure ports up here, the columns of water in this manometer go up or down, and we can measure that change in distance and relate that to the pressure difference. So once we know the pressure difference across various components of pipe changes, we can understand the energy loss characteristics. And that would translate to things like knowing what size pump you need to drive the flow through those pipe networks. Well, this is our baby blue wind tunnel sitting next to the manometer. I'll scoot back out so we can see it, right? That wind tunnel we call our baby blue wind tunnel. That can go up to about 100 miles an hour. And we have another experiment working with manometers inside there. Let's see here. So there we have an airfoil in the test section there that we can change the angle of attack. We can change the curvature on it. And if you can see really close, we have a bunch of holes in that airfoil surface. And on the bottom, we can connect those holes to a bunch of plumbing, just some plastic tubes, right? And those plastic tubes, I hope I'm showing this properly, right? Those plastic tubes can also go up to this manometer, and we can read the pressures on those surface of the airfoil, and we can relate that to lift and drag. The holes on the surface, we can understand the lift behavior, which is the vertical behavior on an airfoil that helps the plane go upwards. And we have in the back of that test section something called a wake rake. And that measures the pressures in the wake of the airfoil. And we can measure the same way with the manometer and the tubes. And we can determine an estimate of the drag on an airfoil based on measuring the energy loss in the wake of an object, right? So really simple experiments in Fluids Lab using some pretty simple instrumentation to get some really good understanding of the physics involved. Another experiment we have out here, we have an industrial compressor. And this is actually in our mechanical engineering lab course and our aerospace engineering lab course, to where if you see that orifice plate in the back, right, I'm sorry, not an orifice plate, but that square plate, we can change the position of that square plate, and that changes what's called the back pressure. So a compressor works by this impeller. You can kind of see a row of compressor blades over there. That would spin real fast in this compressor. It would increase the pressure, increase the temperature after that section. And you can change that plate to change the back pressure and see how it changes the compressor operation. So you really learn about the machinery and how it operates with different conditions. And guess what? We have another manometer plumbed up to that so we can understand how that works, okay? So that's the standard stuff in this larger room. And now I'm going to show you how our supersonic wind tunnels work, because you get a chance to play with supersonic wind tunnels here at Parks College. So the room I'm going to show you are our supersonic wind tunnels. Basically, back to me. Our supersonic wind tunnels here are called a blow-down wind tunnel system. And we have two of them you might have an opportunity to play with. All of our undergraduates in aerospace, mechanical, and civil engineering that go through our Fluids Lab course get to play with one of our supersonic wind tunnels, okay? And they get to visualize shock waves. What does that have to do with civil engineering? I'm not sure, but it's cool and they love it anyway. All right, definitely applies to aerospace engineering. So it works much like a balloon. When you blow into a balloon and pressurize the balloon, if you open up the opening of the balloon after you pressurized it, it shoots a jet of air out until the pressure in the balloon drains to a point where it can't sustain that jet of air anymore. Well, that's how we get to produce supersonic flow in the lab, okay? We have a couple big compressors right here, those green machines. They compress the air and pressurize the air. And what I'm showing you in this room is 2 compressors, some drying tanks and filtering tanks. So we take all the moisture out of the air after it's compressed. We take all the dirt and dust out of the air. Because if you're throwing supersonic air down a test section, you certainly don't want moisture and dust in there, right? The moisture would actually condense out, and then you'd be shooting supersonic bullets down the test section, which nobody wants that. Okay, so here's the outside tank. We have a 14 cubic meter outside tank that basically was donated to the college. It used to be a railroad tanker that transported liquids that was donated to us. So we pressurized that tank, and you can see how it's plumbed. We got a pipe there going to the side of the building there. All right, now I'm gonna walk around and show you the other side of that pipe that you saw going to the side of our building. Sorry, the light's changing on you. Now, our large low-speed wind tunnel has a really large test section. Our supersonic wind tunnels don't have that large of a test section because it takes a lot more energy to push that flow supersonic. So I'll give you an idea of what this room looks like, right? We have some cranes in there so we can move big parts around, and all this piping helps produce the supersonic flow. So if you can see at the end of that wall there is where that pipe comes in from the other wall. And we have 2 butterfly valves. Let me get around this room. I'll turn around and show you this room. It's a little crowded. That's all right. So these 2 valves determine which way the pipe system goes. This one that I'm showing you is what we call our teaching tunnel, okay? That one right there, that blue one, is what we call our teaching tunnel. And we get to direct the flow that way. Here's a really fast acting valve that would be like, you know, unpinching the balloon so the jet of air goes, that green valve right there. Here's a circuit that conditions the flow. And then here's I'm just lifting you up to get around the equipment here. Here is the test section where you guys can visualize shock waves. And the way that we visualize shock waves is the flow goes supersonic over that 2-dimensional wedge there at the bottom left of your picture, right? And it creates a shock wave structure on that tip of that leading edge, okay? And the shock wave structure will be dependent on the Mach number of the flow going through this test section. And what we do is we turn off all the lights in the room and we can actually visualize the shock structures by using what's called a Schlerin system. That's a high-powered light there that bounces off one mirror. This thing's a mirror, right? It collimates the flow, so the light then travels through the test section and across the shock waves in the wedge. We have another mirror, that circle right there. That mirror bounces it off a knife edge right here and across another mirror. Think it like it kind of bounces around until it shows that shock wave. And we have paper on the wall over there where we can actually draw the shock waves that we visualize. All right, so shock waves, when you go supersonic, they can change the properties of the flow dramatically. The pressure skyrockets across a shock wave, the temperature skyrockets, the density skyrockets across a shock wave, and we can use this light trick to visualize the shock wave because the density changes. If you've ever seen a straw in a glass of water, it looks like the straw's bent, but it's not really bent, right? At the water, where that water meets the air, that's because light changes direction as it changes from one medium density to another medium density. Density is the important thing, right? So light actually bends as it hits the water, and it makes the straw look like it's bent. We can use that idea to visualize the shock waves. As we pass the light through that test section, where a shock wave changes the density of the fluid dramatically, the light actually bends and creates shadow patterns of shock waves. I really encourage you guys, again, I'm not running that experiment because it'd be way too loud and you couldn't hear me in here, but I really encourage you guys to YouTube shock waves, Schlerin system and shock waves, and you will have a chance to play with one of those and visualize shock waves when you come here to Park College. Other thing in this room, I know I'm running low on time, so I'll try to hurry up, is you can see behind me all that big black piping. And I've got to give a shout out to Boeing Company here in St. Louis and Honeywell Aerospace out of Phoenix, Arizona. They helped us, we're very fortunate to get some research funding from those guys. And we had a few female PhD students designed this wind tunnel system, and we worked with some local manufacturing companies to make all this equipment. So we actually get to study jet engine aerodynamics here at Parks College. That could be you, okay? And later in a few minutes, we'll introduce you to Justin, who's a senior aerospace engineering student who works in the lab here with me. He's also in our 5-year BSMS program. And we'll introduce you to Jackson, who's a sophomore aerospace engineering student. And I think I'm gonna try not to trip getting out of this room while I'm holding my laptop. And I think this would be a good time to introduce and have you guys a chance to talk to Justin and Jackson.
I guess I'll go first. So I'm like Dr. McQuilling said, my name's Justin Fantroy. I'm from St. Louis. Like he said, I'm in the 5-year Aerospace Engineering program, which means you typically would go for a bachelor's degree in 4 years, but you just go 1 extra year to get a master's. I think a couple of the things that brought me to Parks was just honestly in general, financial aid. They're really good about providing financial aid where it's needed. And considering the financial aid package and the fact that it's a pretty good engineering school and the fact that I'm from St. Louis, it just seemed like a really good fit. And I was just really comfortable on campus here. As far as getting involved in engineering, I kind of always thought about doing engineering because I like, building and working on things and seeing how things work. I was one of those people to like take apart remote control cars and like try to put them back together in different ways. So I kind of felt like engineering was kind of where I belonged. As far as picking aerospace, honestly, it just seemed really cool. It just seemed neat. Jets, rockets, that just seems like a cool thing to be involved in. So that's pretty much how that story goes. And as far as the research and internships I've been involved in, research, I'm involved in the wind tunnel lab, like Dr. McQuilling said. And I actually haven't had internship experience, but that's because I was supposed to be an intern with Boeing this past summer, but that didn't actually work out because the people I was going to work with decided not to have interns just for safety reasons. Makes sense. But I think just in general, being the involvement at SLU, whether it's with like clubs or research, it's one of the best things that I've found. It makes me feel really comfortable. Professors are really open to you wanting to learn, and kind of how I got involved with Dr. McQuilling, I pretty much just said, I'm interested in wind tunnels, and here I am. So like as far as getting involved, it's really easy to do, and it's really fun, and it's a great learning experience. And I'll pass it off to Jackson.
Hello, everyone. My name is Jackson, and I am also an aerospace student. I'm a sophomore, and I am from Union, Missouri, which is about an hour to 45 minutes away from St. Louis. And what brought me to Parks was really, I really enjoyed the fact that it had small class sizes and there wasn't a lot of people. I wasn't just another random person. I know pretty much all my professors on like a personal basis. So it's really nice. I always feel like I can go talk to them at any time I want. And I really like that. And also the opportunities here at SLU are like really great at Parks College, getting involved in research in different clubs and things like that. And the reason I chose aerospace engineering is kind of like Justin said, it just seemed really cool. Like I really wanted to know how things work and how things fly and stuff like that, and be able to work on that someday. So that's kind of why I chose aerospace. And then lastly, I think that's actually about it. Yeah.
Awesome. Thank you, Jackson and Justin, for being here with us. Dr. McQuilling, thank you for that lab tour. That was awesome. So much stuff to see. If anybody has questions, please submit those to the Q&A now. We have just a few minutes, but I'm going to kick off with a question that I hear pretty often. Dr. McQuilling, can you just differentiate between subsonic and supersonic for us?
Oh, for sure. So, oh man, I'm holding the laptop. I use my hands to teach and talk a lot. So subsonic means below the speed of sound, and supersonic means above the speed of sound. So anytime you're above the speed of sound, shock waves are involved, right? And some of the research that we were doing for Boeing, I walked out here in the hallway. So Boeing, they make this, let's see here, this F-18 Hornet. These are just pictures out in the hallway, right? This F-18 Hornet has this engine inlet here. We were studying some of the shockwave structures of supersonic flow that would exist in some of those inlets. And the F-15 has this rectangular inlet as well. That's what we were studying, some of the shockwave structures that, that exist in that inlet there, right? And while I'm at it, let me take you down the hall and show you this cutout of an engine. So this is kind of what jet engines look like and what they work with, okay? So there's a fan that brings in the air and raises the pressure a little bit. Then there's all these wheels that spin around called compressors, right? Just like I showed you in the lab earlier, that increase the pressure for the combustion process. That's where the fuel is ignited and all the energy in the fuel gets released into the gas stream. And then we were studying, these are turbines, just like you have a wind turbine that gets spun by the flow and turns a shaft. And wind turbines, that shaft turns a generator to produce electricity. But in a jet engine, after that energy is released by combustion, that flow goes around these turbines and spins it, and it's connected through a shaft through the engine. So these turbines extract energy to power the upstream stuff. Flow in here is mostly subsonic. It goes supersonic at certain points. And that's kind of the stuff we were studying with Honeywell, right? So supersonic, faster than the speed of sound, and you get shock waves.
Thank you. Justin and Jackson, can you talk a bit more about your career goals, career plans, what's in store for you next? Justin, if you want to go ahead and take that first.
Sure. Well, since I'm a senior, that kind of career goal thing is kind of nearing. I'm gonna start getting into industry pretty soon. After my 5th year, getting the master's degree. I mean, being involved in the supersonic wind tunnel lab is like, it kind of shows that fluid mechanics and things like that is just really interesting to me. And so I think I would be happy to like be involved in any kind of like wind tunnel testing. And I'm actually in a class right now called CFD, which is computational fluid dynamics. And that's basically doing all the things in a wind tunnel on a computer. And so you can measure how like each air parcel interacts with the next air parcel. And that's really important for like any kind of design of anything, like Dr. McQuilling said, anything that deals with fluid contact. So planes, rockets, cars, any of that. That stuff seems pretty interesting, and being able to like sit on a computer, and I mean, sitting in front of a computer is kind of boring all day, but if you have something as cool as fluid dynamics on there, I think it's pretty neat. McQuilling will like that.
I like that.
Yeah, I think kind of like what Justin said. I'm just a sophomore, but I'm really excited to get involved in industry, and hopefully that's sooner rather than later. Looking for some internships over the summer. I just applied for one at NASA, so we'll see whenever we hear back from them. But I really like the fluid stuff, and I don't know if I mentioned it earlier, but I am also involved in the Supersonic Wind Tunnel Lab. And I just talked to Dr. McQuilling, and he was super open and let me join the team. And I've loved that. And that's something I definitely would like to pursue in industry as well. So, but we got a little bit of time to think about that. So.
Definitely. Seems like you have a lot of options available to you and lots of different paths you could take. Dr. McQuilling, if you could just briefly talk about both the mechanical engineering and the aerospace engineering focus. What are some of the careers that students from those programs choose to pursue?
Aerospace is an easy one, so I'll start with that one, right? So aerospace engineering, as I showed you on the slides earlier, is all about spacecraft and aircraft and rockets. So everything that has to do between material selection and performance and operation and mission selection, and not just the aircraft or the rocket itself, but all the launch facilities as well, right? So aerospace engineering, in my opinion, is really mechanical engineering only applied to aircraft, spacecraft, and rockets, okay? Mechanical engineering, in my opinion, is the most broad engineering there is. Even myself, I was good at math and science, didn't know what I wanted to do with it. I started in mechanical engineering because they told me it was the most broad, and you can get into many more careers. So any careers with machines, any careers with moving parts, that's all mechanical engineering. And where aerospace in kind of the last couple years, the program goes off into all the specific applications related to aircraft, spacecraft, and rockets. Mechanical engineering teaches you more about materials and design and manufacturing, right? And that's kind of where they branch off a little bit earlier than the third year, but basically the third year they branch apart from each other. And ME is more about heat transfer and thermal fluid physics and design and manufacturing versus aerospace engineering.
Wonderful, thank you. Yes, so
We
many.
talk all day about it, but
so many things. Unfortunately, everyone, we are just about out of time. So I want to send a huge thank you to Dr. McQuilling for taking us around the lab space. Thank you to Justin and Jackson for being here and sharing your perspectives. And thank you to you for visiting with us today and visiting the Wind Tunnel Lab. So as always, please reach out to us at parksevents@slu.edu if you'd like to further connect with us. And we do have 2 virtual events next week that we hope you will join us for. On Monday, September 28th will be our virtual Girls in Aviation Day. All students interested in aviation are invited to attend this event. From 9 a.m. to 1:30 p.m., we will have a Young Women in Aviation panel, virtual guest speakers from several aspects of the industry, and 3 phenomenal keynote speakers who will be sharing their experiences in aviation with all of us. So join us for the entire day or just a portion. We will be recording that event and posting it to our YouTube page as well. For more information and to get signed up for Girls in Aviation Day, please send us an email at parksevents@slu.edu. And second, next week, we'll have another installment of our weekly webinar series on Thursday, October 1st at 11 a.m. And we will be visiting the Center for Sensors and Sensor Systems with our computer engineering program. So between now and then, we will practice saying that title a little quicker. But thanks again for joining us today and have a great rest of your day.